Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Peter Steenkist, who's a professor at CMU, professor of computer science and electrical and computer engineering. He's been at CMU for more than 20 years, and this is your second visit to Microsoft, which is quite less for someone that senior. So he's worked on lots of stuff, including Nectar, which is very high profile. You had a bunch of SIGCOMM and ISCA papers, and very recently a lot on wireless networks. Today he'll be talking about some of the innovations that he and his group has done in this space. Yeah.
Great, thank you. So, okay, so the motivation for the work I'll talk about is basically something that we called chaotic wireless networking. So the project started about 5 years ago, and when we made the observation that a lot of the wireless networking research was looking at what you can call wireless in challenging environments, with which, roughly speaking, ad hoc networks, with nodes having difficulty reaching each other, very low battery, types of devices, a lot of random mobility, and so on. And in reality, a lot of people were using wireless, but they were using wireless in what were effectively, or looked to us like, very dense environments. They were using wireless at home, in hotspots, in office buildings. And so the challenges in these very dense environments are really very different from the challenges in these very sparse environments. So we basically decided to start a research project in that space, and since the name ad hoc was taken, we figured we call it chaotic. So some of the characteristics of these networks are that if you look at home networks and a lot of hotspots, they're largely unplanned. Okay, people put the access point where it's convenient. People who set up these networks don't know anything about wireless networking. And then also a lot of them are unmanaged, right? And there's also a lot of them that are unsecured. So these are very different environments from, let's say, a campus environment where there are tools available and knowledgeable people available. So that's kind of the motivation and the background for this research. These are data that is from 2005 and earlier, and it basically shows that there are indeed very high densities in a lot of cities, and I think many of you have experienced this yourself. If you're in a hotel somewhere, you pull up your window and you can see a lot of access points. So here's kind of the roadmap that we put up roughly 5 years ago. It was kind of a three-stage plan. The first one was to say, look, today we have a lot of Wi-Fi hardware available. There's a lot of parameters that are in fact exposed, so you do have some control over how these networks operate. Let's see whether we can auto-optimate or automatically optimize, have the network be self-optimizing using today's hardware. And so there's things like channel selection, transmit rate selection, transmit power, CCA threshold, and so on. And so that was kind of the first step. Even at the time, there were some emerging technologies that looked very exciting. So MIME would be one. Directional antennas is another. Software radios is another. So these were technologies that were really not commercially available, or at least not at reasonable prices, but that opened the potential of giving us more control than what we have here, right? And so that's kind of the next phase. And then finally, a lot of these technologies have very limited control over the spectrum because they have to operate in the unlicensed spectrum. And so then at the time already, we kind of say, look, eventually we want to get to more dynamic spectrum sharing type of an access, right? Now, we haven't really done too much here yet. We've been in this space. I'm going to be super conservative today, and I'm going to talk about these topics. So I'm going to talk about results. So it's not this, but these yellow topics here. So I'm going to specifically elaborate on 4 projects, CHARM, PRO, Transmit Power Control, and Directional Antennas. I'm going to be at a very high level on each of these. And the reason is that when I'm through this, I'd kind of like to get back to some common themes that cut across these 4 classes of optimization, because ultimately these things are not completely independent, they are interrelated, right? And so I have a bunch of slides where I kind of look at what the differences and the similarities are between these different techniques. Before I do that, I will actually briefly talk about another project, which is the wireless network emulator, in part because I'll present a lot of results that were collected on that platform. And so EOR is involved in the wireless network emulator, for example. She was also part of the CHARM effort. So let me start with an anecdote. The wireless network emulator was actually motivated by kind of the chaotic wireless optimization. A lot of people have looked at this particular problem. Suppose I have an infrastructure network. I have two APs in red, I have a bunch of nodes, and I have a severe imbalance in the load, right? Well, we all know what you can do. You can basically move some of the clients from the busy AP to the AP that does not have a lot of load, and hopefully everybody will be happy. This means that some of these clients will connect not to the IP that has the strongest signal, but to the next strongest or something like that. So the student who was looking at that at the time worked on this, came up with this algorithm, and then the question came up, how do we evaluate this? Okay? And so, well, we can deploy it, but it turned out that that's pretty hard on campus because we need to modify the campus infrastructure, and people are kind of protective about this. And we could also deploy our own infrastructure, but then we'd be competing with the campus infrastructure. We could do simulation, which the student in fact ended up doing. But this was a very honest student, and he said, look, if we do simulation, I can make my results look as good as you want them, right? If you want a factor of 1,000 improvement, I can probably make it work, okay? And so there's a problem with simulation, which is that if you give the person running the experiments complete control over everything, including the model of the physical world, it becomes very hard to justify your results. So that kind of got us going on the wireless emulator project, where we basically observed that there's kind of this trade-off between testbeds and simulators, and I don't think I have to elaborate too much on this. I think you know this. Testbeds are more realistic, but repeatability and control are very difficult. Also, testbeds tend to be tied to a specific location, so you can only collect experiments in that location. Simulation has a lot more flexibility, repeatability, easy control, but you have a question of realism that you need to address. And so what we basically came up with was this design for something called an emulator, which would try to achieve kind of the good parts of both of these worlds. So here's kind of how this works. Some of you are familiar with this project. So the idea is that I use real hardware because I am building a testbed. So I use commercial wireless devices or custom-built wireless devices. It doesn't matter. I take this device, I take off the antenna, and then I plug a coax cable in the antenna port, and I capture the signal that is transmitted by the device. Then I would have what looks roughly like a software radio front end, which basically takes this signal, brings it to an intermediate frequency, and samples it at a high rate. So I get a digital representation of the baseband signal. And then I basically do that for a bunch of devices, and I inject all these signals into an FPGA, which models the effect of signal propagation. So it models attenuation, fading, interference, noise, multipath. And anything you can program, you can do, right? In fact, the physical world isn't really constrained here either. And then basically for each of the target devices, you kind of regenerate an input signal that you pump back into the device. So that's roughly speaking what this looks like. There's a bunch of red stuff here, which is very important. It's very important that you isolate your testbed at the signal propagation level from the environment. Okay? The other thing, it's very important that these laptops can only talk to each other through your FPGA. They cannot talk to each other over the air, right? Or these are two additional constraints. So it turns out that building this is actually quite difficult. You need to really deal about the issues such as the fidelity of the signal as it propagates through the testbed. One of the things is that you need a lot of flexibility because that's kind of the whole point of the testbed. You want to be more flexible than something that's in a specific location, and you want to have this control and repeatability element. And then for a bunch of computer science people, doing things like system building and packaging and so on turns out to be quite a challenge. However, the student who actually did all this initial design and also was the main architect here was Glenn Judd, and he made this happen. And now we have both Eeyore and Kevin Boris, another student who are continuing the project. But this is what we ended up with. So we have these devices. There is what you look at an RF front end that brings the signal to an intermediate frequency. This brings it into the digital domain. This is our FPGA. Then we also have a controller that is used to control the experiments. Okay, so that's the system that we built. The system we have has 15 nodes rather than 4. Yes?
You mentioned a couple of slides ago, like, wouldn't it be nice to actually feed in the background interference into the emulator? Like, instead of all the signals coming from the controlled experiment that you're doing, if you wanted to study,
yeah.
Is there a way to do that?
Yes, can I get back to this in a minute? Okay. Actually, I think I took out that slide, but the there's a bunch of things that would be nice to have, and I'd like to talk about them all together. So this is kind of what it looks like. This is what the RF front end and signal conversion card looks like. So, I mean, you can see it. It's real cards. These are both custom cards. Then basically these are combined with a laptop, which, is one way of doing it. The blue stuff is the RF isolation foam that you need to isolate the device, or to isolate all the analog parts. Then this is the central FPGA, which is a Xilinx FPGA, with a lot of connectors to connect to the endpoints. And then this is all rack mounted and looks as follows. So that's kind of what this all looks like. Question I often get is, well, okay, this is all good, but how does this really differ from a real test bed and a simulation? So this is kind of a visual representation of this. It shows the protocol stack going all the way from signal propagation at the bottom to the applications at the top. And then if you're running in the real world, everything is obviously real, right? So that's easy. Simulation, everything is simulated. There are some efforts where you take things like real protocol stacks and embed them in simulation. So that's why these blue wiggly lines are here. And then in our system, this is all real, and then this is basically emulated. Okay, and this gives us the control over the signal propagation environment here. This is the antennas and the signal propagation itself. And so, of course, one of our things we need to be consciously aware of is this needs to be realistic for our results to be valid. There's some related work which I've mostly touched on. And then this is actually being operated as part of the Genie project right now. And we can talk about this offline. But let me use this slide to briefly elaborate on two extensions that we really would like to get to. The first one is that in the current environment that we have, the FPGA basically is controlled at the channel level. People basically need to specify the behavior of the different channels. It's clear from a lot of our users that they don't have the background to do this properly. So what we really need to do is raise the level of abstraction. And so what I'd like to do is build a layer on top of that. Basically says, look, a user can say, give me an office environment, and give me a vehicular environment, which we were talking about before, or give me a mountain, or whatever, right? And so that would be one thing. The other thing is that 15 nodes is kind of very little or a lot, depending on how you look at it, okay? But it would in fact be nice to say, look, I have a 15-node experiment, but I would actually like to model the interference of, let's say, 15 or 100 other nodes, right? And so this is something that can be done. The most likely way of doing this is probably to use one of the nodes, attach a software radio on it, and then have some software on it that plays back traces or does something to model the interference. The more tricky thing here is that the interference observed by the 15 nodes is not going to be the same everywhere. So you do need to be kind of, there's a little bit more complicated than it looks, I think. So these are kind of the two major extensions that we'd like to look at.
So what's the scalability of the system right now? It's 15 nodes.
It's up to 15 nodes, right? This is limited by the card.
Why is it 15?
It's just simply what we had funding for. It's simply what we felt we could build in a university. Also, the bandwidth of the system is very wide. It's the full ISM band. It's 80 megahertz. If we would build an emulator that operates on 20 megahertz, then we probably could do a lot more.
Let's say so if you're using a Vertex too. If you went to a better FPGA, would that solve some of the issues?
Obviously, yes, it would. But it's not the only thing, right? The packaging is in fact quite tricky. If a company built it, that has experience with analog systems, I think that would be an entirely different matter. They could build bigger systems easily. Yeah. Okay, so let's talk a little bit about the 4 projects, and then I can try to kind of give a more global perspective here. So this is some work that was done by Glenn Judd and Eeyore. So I think we all know the problem. If you look at Wi-Fi, for example, and many technologies, they have transmit rate adaptation, where they dynamically pick the best transmit rate that they can use. So if you have an SINR graph here at the bottom, and you have a packet reception rate, you end up getting these curves. And if you pick a certain if you observe a certain SINR at the receiver, you can then say, okay, which transmit rate would be the best one? You want to be as much to the right as possible because those are the higher transmit rates. But you obviously want to have a high packet success rate, so you may pick 5.5. Okay, so I think we know how this works. So the visual representation here is that your received signal strength at the receiver will change over time. This is a static pair of nodes here. This is a trace that we replay. So you can now kind of say, okay, over time, I need to jump between these different rates here to get the best out of my channel. This is the easy case. This is for a mobile node, so you also get the attenuation in here that changes as the node moves around. And then the G rates, there are many more of them, so you need to do this type of a mapping. Okay, not realizing, of course, that predicting the future is always a little bit hard. So it turns out there's been a lot of work on this. And so most of this work relies on something that's called trial and error probing. So you basically look at the success you had at certain transmit rates in the last 5 to 10 packets, and you try to use this to predict the future. And so this kind of works, but it tends to be slow in environments that change, like the mobile environment, right? Because you need to see enough errors, and then it's our trial and error. There's some work that has been done in the past where people use the SINR as a way of getting an idea on the quality of the channel. Okay? The most notable problem you run into in that case is that the SINR, which let's assume for a second that this is dominated by the received signal strength, the transmitter is the one that picks the rate, but the receiver is the one that measures the received signal strength. So the wrong node has the information. So there's one, I thought, very good project which basically observed that if you use RTS-CTS, the CTS that can be used by the receiver to inform the sender what rate to use based on the received signal strength it observed. The problem now is, of course, that RTS-CTS is very expensive and it's really not something you want to use. So that's kind of where we come from. So what we basically developed is this algorithm called CHARM, where a transmitter can learn about the rate to use or get an estimate of the received signal strength at the receiver in a passive way without actively using RTS-CTS. And the way it actually does that is by using, okay, well, this is going to be interesting. Okay, we're going to see how this talk goes. Because I modified this and it's not here, so there's probably some stuff that was lost. Anyway, the receiver is basically uses channel reciprocity. Oh, it's right there. Channel reciprocity to do that, and I'll explain in a second how this works. And so we can basically get an estimate of the received signal strength without the RTS-CTS, and then the transmitter can then basically dynamically pick the best rate. It's not quite as simple, but that's kind of the high-level idea. So the way to look at this is our equation, SINR, it's the received signal strength divided by noise plus interference. What we want on the receiver is the SINR, and so we can now it's kind of some simple equations to figure out how you do that. The received signal strength has to be measured by the receiver, but using channel reciprocity, you can actually estimate it on the transmitter, and I have the next slide shows this. Noise is largely constant, so it is something that can be measured by the receiver and it can tell the sender what it is. And then interference we basically ignore because we have carrier sense which should limit the effect of interference. So this is not a perfect solution, but it actually works well most of the time. So then the question becomes, how can I estimate the received signal strength on the transmitter that the receiver observed on the transmitter? And so it turns out that this is actually pretty easy. So the received signal strength is basically the transmit power minus the path loss, and then you have the antenna gains. Okay, so that's the top equation. The path loss is the one that you can get to using channel reciprocity. So basically, if the transmitter A hears a packet from the receiver B, and it knows these parameters, and it can measure the received signal strength, it can estimate the path loss of the channel. That will also apply to the forward path, which is really what it is interested in, and then it can plug that into that equation. Okay? And so it actually turns out that you can measure everything if you know the transmit power by the receiver, which again the receiver can tell the transmitter. Okay? Turns out the antenna gains don't matter because again that's symmetric, that falls out. So it turns out that there are three parameters that are important: the path loss, which the transmitter can estimate based on reciprocity, the noise, and the transmit power, and both of these can basically be provided by the receiver. So here's kind of how these pieces fit together. I have a transmitter and a receiver and a bunch of other nodes. The transmitter and all the other nodes are sending packets, and the transmitter overhears all these packets, and for each of the nodes, it will basically create a history of the received signal strength that it observed by all these nodes. Okay, so for example, this would be the received signal strength history that for the blue receiver as it is overheard on the transmitter. Then using the transmit power and the noise figures, it can actually translate that into an RSSI estimation at the receiver. Okay? And then when it needs to transmit a packet at a certain point in time, it can basically use this history here to kind of extrapolate what the received signal strength may be, or the SINR may be, I'm sorry, right? And so obviously this is a prediction in the future. This is not going to be always accurate, but it is kind of an informed estimate. And then it can basically pick the transmit rate based on a table. Okay? Yes?
Why don't you just send the SNR back in the X?
You don't. Well, you need the SINR for the original packet, right? You need to pick the rate.
The prediction, right? I mean, you can always be your one packet behind,
right.
But that's not.
Well, yeah, you can. Well, it turns out you don't need to conclude that, but because you can use the ACK the ACK is going to give you another data point here automatically. You don't need to include it. You can use channel reciprocity to get it from the received signal strength of the ACK.
Yeah, but my point is, like, you already, I mean, otherwise that would also work, right?
Yes, that would also work. That would work fine too, yes.
Well, I mean, we found in San Francisco taking some measurements that actually the noise floor, thermal noise floor is pretty much the same everywhere. But there was an ambient noise floor due to, microwave ovens and other transmissions from things far away. You could represent as sort of a noise floor, and that was different in each location.
Yes.
And that won't show up in the path reciprocity condition.
So the path loss, the noise floor that you need here,
yeah.
each node in the system periodically broadcasts the transmit power it uses and the noise floor that it observes. We do not assume the noise floor is the same everywhere for exactly the reason that you mentioned. Yeah. So there's a lot more details here that I will not get into because then this becomes a charm talk and that's not the idea. Eeyore can tell you all the details. How about that? And she'll probably do a better job than I do. So we took a lot of measurements, which means Eeyore and Glenn took a lot of measurements in a lot of different environments, and they're listed here. And this is like homes and office buildings and a library and all that kind of different environments. We compared it with the three algorithms that are deployed with the MAD Wi-Fi driver, and this shows you the performance. So purple is charm, so it does pretty well. It turns out that sample rate actually does pretty well too. It's a pretty good algorithm. And then the other two, don't always do that well. Actually, Ono looks pretty good here, but has some problems. We don't always do the best. So this is a case here where actually sample rate is better than we do. So nobody's ever going to be the best always, right? That's not how this works. But generally speaking, we actually do pretty well. We also ran experiments in the mobile environment. So sample rate is really good, but it is a little bit slow in adapting because it needs a lot of samples to decide what rate to use. And so here's charm really does very well. And so you see sample does really well too, but it's very slow in going to the higher rates. Okay, so that's something that many people have observed. This is not something that we observed. And then the final point I want to make is that we also ran a lot of experiments on the wireless emulator, most of which I'm not showing. But one of the interesting things that we can do on the wireless emulator is that we can create artificial heart traces. And one very difficult case for any rate adaptation algorithm is hidden terminals, because the channel is good, right? But because of collisions that you can't avoid, you basically end up losing packets anyway, right? And so I'm not going to go through the details here, but we can artificially create hidden terminal situations on the wireless emulator and then go and compare our algorithms. And we do pretty well here, in part because we rely on the quality of the channel directly, and we don't rely on the collisions. Okay? This is not entirely true, and I will get back to that point later. Okay, so it is 99% true, 1% not true. So I'll get to that 1% later. So that's kind of a very quick, high-level overview of charm. Okay, and so let's now talk about a different project, which is work that was done by Amy Liu, who's actually defending her thesis on Monday. So this is something called PRO. Actually, some people are here at Microsoft are familiar with this. So the idea is very simple. Suppose I have a sender sending a packet to a destination node here. The packet transmission fails. The traditional Wi-Fi approach is to say, look, the source will retransmit the packet. Okay, that we all know this, of course. But however, there can be a bunch of nodes in the environment that are in fact closer to the destination and have more specifically a better channel to the destination. They may actually have overheard the packet. Now, those nodes may be able to be in a better position to retransmit this packet rather than the original source. And in a better position maybe for many reasons. One of them is they have a better channel, so the packet success rate is better. The other possibility is they may be able to use a higher transmit rate, and so the efficiency of the retransmission is better. Okay, so that's kind of the idea. So we kind of have a source, sends a packet. If the packet transmission fails, one of these relays will notice that the packet was lost, will realize that it has a copy, and it will basically retransmit on behalf of the source. Now, the obvious problem here is, of course, well, how does the source know this is going to happen? Also, there may be 5 relays that overhear this packet. How do you make sure they don't all retransmit at the same time and you have massive collisions? And so these are the types of problems that you need to deal with. One of the things why this actually turns out to be a very potentially very interesting is that things like channel fading and shadowing are very channel specific, right? So over time, who has the best channel to the source, which of the relays has the best channel to the source and has the best channel to the destination is going to change, right? And it's going to kind of move around. The best one's going to move around over time, and you want to really, for every packet, pick the best one. That's the whole idea. Oops. Okay, so here's the idea. So we use, this is really meant for infrastructure mode networks, and you only use multi-hop if there's a transmission failure. The whole goal is that the retransmission success rate goes up, okay? And then the challenges here are marked in red, so you need to efficiently identify and prioritize relays. You need to avoid increases in collision rates, because now more people can be retransmitting these packets. And there's kind of an interesting question of how you deal with fairness, and I'll explain how that works in a minute. So, the way, there's been some work in this area, related work in this area that I'm largely not going to talk about, but there's been work that has done similar things, and the way they resolve some of these issues here is by explicitly coordinating between the relays. Okay, so they say, somebody will say, oh, I have a copy of the packet, I can forward it, and then they kind of coordinate, and then they do the retransmission. Pro, on the other hand, relies on the existing random access techniques that Wi-Fi has. So there's already a mechanism in Wi-Fi where you have a back of window, and nodes independently pick a value in the back of window to minimize collisions. There's also a notion of exponential backoff where this back of window grows over time. Okay? So the way we basically do it is we basically rely on the existing multiple access mechanism that Wi-Fi has and the carrier sense mechanism to basically avoid that we get too many collisions. The second thing that we do is we actually rely on signal strength to prioritize the relays. And so I'll explain how that works in a second, but all else being equal, we would really like to have the relay that has the best signal strength to the destination, but did hear the packet, is the one that does the forwarding. We don't want to have some random relay that may have a very poor channel to the destination do the forwarding. And then finally, it turns out that we actually can control fairness, and I will explain that later. So here's how this works. We basically have a background process on the left, and then we have the process that is used after a packet failure on the right. The way the background process works is that every node kind of listens in on traffic and basically uses RSSI as an estimate of the channel quality to both sources and destinations, or potential sources and destinations. And so they create this per node RSSI history, which is not all that different from what Charm does, in fact. then what they can basically use this RSSI history for, after some tuning, which I will largely ignore for now, they basically decide whether they're actually, which source destination pairs they're good relays for, which means that they have a pretty good channel to both the source and the destination. And so then for those source destination pairs, they will actually periodically, like once a second, broadcast the channel quality they have to the source and the destination so other relays can overhear this. Okay, so that's the background process. So then when a packet transmission fails, a node will observe this because a relay will observe this because it hears the packet but not the ACK. Right? So then it says, okay, there's a packet loss. And then it says, look, am I basically, then it goes to its database and where it has information about all the eligible relays and their channel quality to the source and the destination. And then everybody goes independently in a distributed fashion through a process where they figure out whether they're kind of one of the better relays. Okay? And then when they do that, then they will also go through some kind of prioritization where they say, look, do I have the best channel to the destination? And then there would be a high priority relay, or do I have kind of the second or third or fourth best channel and they are a lower priority? And then they basically decide whether they participate in the retransmission process. So that's at a very high level how this works.
How would this interact with charm, though?
That's a question for later. Okay, this is a very good question. It's actually a hard question. But so that's roughly how this works. So and I'm actually going to use the picture to explain this in a little bit more detail. So the process would be here. I have 4 relays. They assume they both have a reasonable channel to both the source and the destination, so they are qualified. And then based on the periodic broadcasts, they may all observe that these 3 relays are actually in pretty good position to do forwarding, and this one isn't. So this one would withdraw, would not participate in retransmissions. These 3 would actually consider themselves as good candidates for retransmission. One of the problems that you now have is that 3 may be too large a number because your collision probability goes up as you have more relays, right? And so now, how do you trim down the set? Well, that depends on the likelihood that these nodes receive the packets, overhear the packet. So depending on the quality of these channels, the nodes are going to decide independently what is the best subset of people to actually participate. So you want to keep it small, but large enough that you have a good chance to get a good path to the destination. So that's kind of the balance that we're looking at. And then the other aspect is the prioritization. Okay? So the way the prioritization works is actually also just by leveraging the behavior of the Wi-Fi, in the sense that every node can basically rely on 802.11e, which some of you are probably familiar with, but it allows you to basically have different nodes pick different initial backoff windows. So some nodes can pick a backoff window of, let's say, 16 slots. Others can pick one of 32 or 64 slots. Obviously, if you pick a smaller window, your chances of retransmitting first go up, right? And again, it's statistical, right? It's random. And so that's how Pro does that. It assigns different initial backoff windows to different nodes. So here's kind of an experiment that I think will maybe bring some of this together. So I have a setup. This was done on the emulator, a source and a destination. The relays are spaced 20 meters along a line, okay? And I'll show experiments where the source is fixed, but the destination is placed near different relays, okay? And so here's kind of that's how that works. Okay, very nice. And then this is kind of the results we get on the emulator. There are 4 graphs here. There are graphs that only have attenuation, no fading, and then there's graphs with fading, which are the red ones. So what we're seeing is behavior that actually matches our intuition pretty well. If you have only attenuation but no fading, it's a very static environment, right? And it turns out that Pro really doesn't work except in the case when the source and the destination are almost out of range, right? Because in this case, you're almost creating a mesh topology here, right? And so what you're seeing is that for nearby situations, Pro makes no difference, and here Pro effectively becomes a mesh node that forwards the packet. But the picture is different for fading, because what's now happening is we're getting a more dynamic aspect where some relays overhear some packets and other relays overhear other packets. And now you're seeing that even for the nearby situations, which is still pretty far, right? What you're seeing is that Pro can still already help because there are packets that just because of the fading, the destination doesn't hear, but intermediate nodes do hear. Okay, and so it kind of matches what I think the intuition we had, but this uses real hardware and it's in this emulated environment. Some more results here. The first two bars, the blue bars, are Pro. Let's ignore the Pro optimal for now, and then we have Charm. At rate adaptation, I think that was a part of your question. Sample rate as a different rate adaptation algorithm, and just plain Wi-Fi with fixed transmission rates. So this kind of confirms this. If you only have attenuation, then Pro doesn't make much of a difference. Okay. If you start to have fading, then Pro actually does help, and it actually does better than the rate adaptation algorithms. And then as the fading goes up, you really, relatively speaking, the gap also increases. Okay, so it matches your intuition. I'm actually going to skip some of the other results. We can talk about fairness offline. And what I want to get to is that we also ran experiments, or Amy ran experiments, in 2 buildings on campus. This is one building, which is Porter Hall. So what she did was she basically put up 10 laptops. And now what she did is, for each pair of laptops, she used that as a source, as a destination, ran an experiment, and then the other 8 nodes are relays. And then she picks another source destination pair, and the other 8 nodes are relays. And she went through all the combinations. Okay? And so the results you get for this particular environment are shown here. It's basically the cumulative probability distribution of the fraction of the nodes that observe a certain throughput. Okay? So throughput goes up left to right here. So there's a certain group of nodes, about a third of the nodes have very good connectivity. A third of the nodes have very lousy connectivity, and a bunch of them are in the middle. These are nodes that are effectively out of range because of the environment. These probably have more or less a reasonable line of sight path, and these are in between. So what we're seeing here is kind of 3 things. The first one is that for the good nodes, Pro is in blue. It overlaps with sample rate in this case, right? And so this is very good. It means that Pro doesn't hurt performance, which is not necessarily a given. Then what we're seeing here is that for the very poorly connected nodes, it turns out that Pro actually helps. And this was never our intention, but it turns out that Pro can function as a range extender, right? It extends the range of the radio, okay? And you can achieve better effects or similar effects using mesh forwarding. This gap we can talk about offline, okay? This is a detail of the implementation. And then in the intermediate range, where you have an okay channel but not a great channel, that's kind of where Pro also helps, right? And these were, by the way, these experiments were actually done in this building, which has hard walls. It's a traditional office building. Also, this was done at nighttime. So she also ran experiments in a different building, this is the graph she got. So the thing that's interesting is this graph looks completely different, right? So it turns out that Pro almost always works. We never have the out of range situation there. These results were actually taken during the daytime, and so there's a lot more mobility in the building. In fact, this is in a very busy area of the campus, and so there's a lot more fading here. And so what we're seeing is that as fading goes up, Pro basically helps, right? There's also issues of line of sight that are different, but you know, we kind of just want to give you a high level picture here. So this works pretty well. The interaction with rate adaptation is something I want to make part of the conclusion discussion. Okay, so the next 2 sections are actually shorter, so that will go hopefully work. So this is actually fun. Let's do this. So what we want to do is use transmit power control to reduce interference. This is the next thing. This is work that was done by Chi Liu, another student in our group, and this is together with Srini Seshan. Okay, here's kind of the NS2's view of the world, right? I have a transmitter. Suppose I have 2 other nodes. This is my intended destination, and this is the poor node that suffers interference from me. So what should we do? Well, I think this is obvious, right? If I reduce my transmit power, then I can still reach my destination, but this node no longer suffers interference. So the intuition here is that reducing transmit power is a good thing, right? Okay, very good. Now, when I talk to people in the EE department or ECE department, they have a different story. They have this SINR equation, which I already put up. Now, when I look at that and I reduce my signal power, all else being equal, that's really not such a good thing because I'm moving to the left on this axis, right? And reducing my transmit power is a bad thing, right? So now the research community is using both of these models. And so clearly somebody has to be wrong here, okay? So the question was who, right? Well, it's the hardware that decides this. It's not us, right? So we actually ran some experiments on the emulator. Very simple experiment. We have two node pairs. I have a source and a destination, and then I have an interfering source that I've created a hidden terminal here, okay? So they can't hear each other. These guys send at a certain transmit rate that we change over time to create a curve like this. And then I change the transmit power of the interferer to basically create multiple curves. So this is basically the color for picture here at the bottom is what we end up with. Again, this is under highly controlled conditions. There's no multipath here. It's very clear channels. But the thing that's very interesting is that changing the signal power at the interferer basically means that I shift the graph by a fixed amount, which turns out to be the same amount that I change the transmit power of the interferer with. In other words, when I move from this graph to this graph, I can basically do that in two ways. Or from this point to this point, I can do it in two ways. I can increase the transmit power, or I can reduce the power of the interferer, right? So if I now go back to my two models, this is the winner, okay? Because this effectively corresponds to this picture here. There's some details about this graph that are interesting to talk about, but I will actually skip. There are some issues here on why do we have this, and so on, right? But those can be explained, but are somewhat orthogonal to this talk. So basically what she did was, actually, how long is the talk? 5 more minutes, 10 more minutes? 10 minutes, 10, 15 minutes, okay. So she basically then wanted to do transmit power control. Again, there's been a lot of work in this area, well, a fair bit of work in this area, but most of it is doing per access point transmit power control. So you're assuming you have no control over the clients and the access points control the power, which is a perfectly valid thing to do. So she wanted to be more aggressive and wanted to basically say, look, every link independently adjusts its transmit power and the CCA threshold, okay? So basically the starting point for his work was a very simple observation, which is the following. I can take a transmit-receive pair where I have, let's say, AP1 talk to a node and I have AP2 talk to a different node. Then there's also interference that is created through the dotted lines there. What I can now do is if I have control over the both transmit powers, it turns out that you can try to tune both of the transmit powers so that these two transmissions can happen simultaneously. Because that's really what I want to be able to do. I don't want these things to defer to each other. I want them to transmit independently. And so using the SINR equation and by ignoring noise, because most Wi-Fi networks operate way above the noise floor, so noise is not an issue, it turns out that you will be able to tune the transmit power of AP1 and AP2 if this condition holds, okay? And then obviously the SINR in both of these cases includes both the signals the signal strength at the receivers from both of the APs. So you can go through the math. It's simply based on the SINR equation, right? So when you look at this, there's two conclusions. In some cases you can't do it, but in other cases you can, and you calculate what the transmit power is that you need to do this. In fact, there's not just one value that is true. There may be multiple values that work. So then what he did was basically say, okay, how can I now use this? Yes?
What do you mean by possible? Like, what exactly is when you say possible, is it just that you will get a reception, or is it better than sequential, or?
The goal here is to have the two transmissions happen at the same time, right? That's the goal.
And still do better than going one by one after another?
Well, I'm assuming it's always better than doing one by one, right?
Why do you assume that?
Why do I assume that?
Yeah.
If I can do two transmissions simultaneously, it's going to take less time than if I do one after the other.
Interference.
Yes, no, the whole idea is that you pick these values so the interference doesn't prevent reception. So, okay.
An auto rate system, right? So
It's what?
In an auto rate system.
Yes. Yeah, let's keep the auto rate out of it for now. Okay.
Okay.
Yeah.
So it's just
You want
a
what
fixed
you are.
target rate.
Yes. Let's assume it's fixed or a small number of values or something like that. Yeah. It turns out this problem is hard enough without auto rate. So then what we basically did was to say, okay, can we basically improve spatial reuse and come up with an algorithm that builds on this to do this, right? So it turns out you can. The way it basically works is that you, the way you do it is that you basically build a pairwise conflict graph for your network, and then you can use the equation that I had before to remove links from this pairwise interference graph. And obviously the more links you remove, the more transmissions will be able to go on in parallel. Now it's important to realize that this is a kind of probabilistic optimization in the sense that it may be that you remove a link between two transmitters who are actually transmitting to a specific destination. It may be that they never want to do this, right? But if they do, then removing that link will basically enable that. And so there's then also a distributed version of this algorithm that he came up with, which gets quite tricky because you need to have a fair bit of information sharing going on. It does not create a global interference graph. Each node builds a local interference graph. So there is that going on. And I will not, it really is hard to explain in a short amount of time, so I will not do that. But it can in fact be done fairly easily. And then again, he ran some experiments. So here, there's a number of different solutions. There's a manual solution that is shown with this being the individual throughput. The orange bar is what you get if the two go on in parallel. Then manual means manually optimized. You literally did an exhaustive search of all combinations and came up with this. Here there's different combinations that don't use our algorithm, and here's our algorithm. And the point is kind of that the yellow line here, there's actually very close to optimal in many circumstances, right? Now it turns out there's a really big open question here, is that this is for a particular configuration. I can't argue that this is typical, right? I can argue that it works, but and so we ran a bunch of them, or Chi ran a bunch of them, and they show very similar results. So this is for an 8-node experiment, for example. And as the density goes up, it actually turns out that you do get improved benefits. So this is kind of transmit power control, okay? So a very high level, and I encourage you to go read the paper, or I can mail you the paper if you're interested. Then a final point, which is also work by Chi, is actually to go look at directional antennas. And this is kind of an interesting variant on what I just talked about. I think you all know how directional antennas work, right? It turns out that most of the directional antenna use so far has been outdoors, where they're in direct line of sight environments, where it's kind of an entirely obvious optimization. So this is actually looking at an indoor environment. And so our initial observation was that this may not work, right? Because there's a lot of multipath going on, and the interaction between multipath and directional antennas is a little bit fuzzy, right? And in fact, it's still fuzzy for us. We're still learning over time here. But we were actually able to at least artificially create a scenario in our head that said, gee, maybe indoors is a nice place to use our directional antennas because we can kind of do interesting things here using the multipath. So this is a scenario. Suppose here on the left I have two senders and I have two receivers. Unfortunately, the receivers are close together, and so we have interference that is created by the other sender, okay? And we can't have simultaneous transmission, even with transmit power control. You can now say, well, wait a second, maybe because of the multipath, the two senders can actually be directional senders. They can point in a different direction, which is not the most obvious direction, and you get something like this, right? So now this is a cartoon, right? So I don't know whether this ever works, but at least on a cartoon level, this is good. And if you can't do it at the cartoon level, it's never going to work. So that's kind of what we did. So he did some experiments, which I will not show, where he actually experimentally tried to determine whether this was ever the case. And indeed, there are cases where if you describe this path as the max SNR path, where the max SNR path was not optimal if you started to have multiple directional antennas. So he then basically came with up with a solution where he say, look, if I now assume an environment with directional antennas in the APs, but plain omnidirectional clients, okay, how can I basically use directional antennas? So it turns out that if I go back to my transmit power control approach, even though we don't change the transmit power here, the way you would do that is by building a conflict graph, and by then using this conflict graph to determine who can transmit at the same time. And we're relying in our topology here on the fact that these APs are connected through a wired network, so we can coordinate them very easily for scheduling purposes. Now, the problem here is that because of the directionality, the nodes in the conflict graphs are not just the links, but also the direction in which the antenna is pointing. So the conflict graph size explodes, right? The number of nodes in the graph goes up by a factor of k, which is the number of directions of the antenna. And so it turns out that building this conflict graph is very expensive. It's an order n times k squared problem. So building the graph is very expensive, where n is the number of APs and k is the number of directions. So there's a lot of experiments to build this graph explicitly. So Chi said, well, this SINR model worked pretty well for transmit power control. Let's try it here. And so the idea now is that you're assuming that the SINR at the receiver is going to be a pairwise, assuming a pairwise interference assumption, can basically be calculated by the difference between the signal strength by the intended transmitter and that of the interfering transmitter, right? And now if I can basically calculate those, or measure those, I can estimate the quality of the channel this way. And so it turns out that the nice thing about this is that the complexity of doing the measurements becomes nk rather than nk squared, right? And so you're basically relying on this SINR model to be able to do this. And so he built this, and I will actually not go through the details, but this actually works pretty well. It turns out that there's another challenge here, which is that you need to reduce the complexity of the scheduling problem. And so this is not really a networking problem. Okay, so that's kind of how that worked. Now, okay, I've talked about 4 topics. And so all of them actually relied in some way on RSSI measurements, right? Which is kind of not something that we envisioned when we started this project. This is something where, you know, when I needed to put a talk together, I said, hey, wait a second. There's a lot of mentioning of SINR in these slides. So how does that work? So most of these techniques seem to work. You know, you can question the value of an RSSI reading or not, but it actually kind of works pretty well. And this is not entirely a surprise. If you talk to people in EE departments, they have an unwavering faith in the SINR model. Okay, and so they've been working on this much longer than I have, so you need to have some faith here. So this is a common theme. The thing that's interesting, though, if you look at the 4 projects, and I hope I've given you enough details on it to be able to appreciate that, it turns out that there are some big similarities, like the SINR model and the RSSI readings, but there are also some big differences between them. And so these are kind of a list of some of the big differences, and I'll discuss some of them in a little bit more detail. First thing that I want to point out is that all of the 4 projects were implemented on Wi-Fi hardware. But these are not Wi-Fi tuning projects because they really sometimes do very weird things, right? These are not standards compliant things. Charm is actually the only one that fits within the Wi-Fi standard, okay? Pro, you know, obviously having other nodes retransmit on your behalf, you know, I think a lot of the people in the IEEE would be offended by this, and possibly justifiably so. Here, we're really not making any assumptions about what the network is. This is transmit power control. This does not have to be Wi-Fi. It doesn't matter what the protocol is. It's protocol independent. Dirk actually uses a TDMA protocol with centralized scheduling, so this is also not, there's no carrier sense use, for example, in this, so this is also not Wi-Fi. So these are very different types of projects. But one interesting thing is that a first observation here is that these 4 projects actually use SINR and RSSI readings for different reasons. Pro and Charm, to a large extent, use it for agility because very quick feedback, right? In contrast, these 2 projects use these readings rather than probing because it reduces the search space in the optimization. So it's really, maybe fundamentally there's all reducing overhead here, but there's kind of a different motivation here. This is an agility argument to be able to very quick, and here it's really reducing the cost of the learning about the environment that's being used. So there's a different reason for that. The other thing that is very different between these, which is I think kind of interesting, is that these operate on very different scopes and timescales. So Pro and to some extent Charm operate on a per wireless link, source destination pair, right? Charm actually is clearly per source destination pair. Pro needs to include a bunch of relays, right? So the scope is very different. Pro is the most adaptive of the four. It's on a per packet basis that it optimizes, right? Literally every packet could be relayed by a different node. Charm is kind of on a burst of 4 or 5 packets, I would say. This is a bit of hand waving, but it's a fairly short-term and quick optimization. These are slow. These are all adapt at the second level, right? Because and the reason is simply that they need to coordinate a fairly large number of nodes in order to be able to optimize this because of the interference issues that need to be dealt with. So the scope here is roughly from a node kind of 2 hops away, right? Roughly speaking, that's the set of nodes that needs to be coordinated. So we have 2 nodes and the nodes in between, a node and up to 2 hops away. So the scope is very different, and then also the time scale matches the scope to some degree. You can be much more agile if there's only 2 nodes involved. The other thing that's very different between them is that the level of precision of the SINR estimates that you need is very different. Charm needs by far the most precise information. If you're off by charm, you're either going to have a different, the rate's going to be wrong, right? Pro actually, it doesn't matter very much, it turns out. We only use this to select the relays, and we typically have several anyway. So if one of them is way off base, it doesn't really matter. So we only need very rough estimates. Here, it turns out to be not particularly sensitive either, because it's one of these things where we opportunistically, if your transmit power control doesn't always avoid simultaneous transmission, then that's okay. I mean, you're no worse off than you were before, right? And so it's not very sensitive. Here, Dirk is actually very sensitive. This turns out to be very tricky because you don't have carrier sense to save your hide, effectively. So it's a very different usage of that information and a sensitivity to the precision. There's very different ways in which they deal with interference. The Charm and Pro basically rely on the existing mechanisms in Wi-Fi or in whatever algorithm protocol you use. Transmit power control estimates the interference and adjusts the carrier sense for that. I didn't talk about this at all, but there's an algorithm to pick the carrier sense once the transmit power control has been done. So it accounts for that, and then it still uses carrier sense because using the optimized carrier sense threshold. Here, we assume that the scheduler has eliminated interference, right? So there's a very different model again. And this is really why the accuracy of the information needs to be pretty good or conservative, right? And then there's something that I have not talked about because this is a detail, okay? But the fact of the matter is your estimate of the SINR will sometimes be wrong. You can be as good as you want, but it will sometimes be wrong. And the problem that you have is that sometimes these failures can be very systematic, right? You can just have a card that's completely uncalibrated or weird, and you don't want to be in a permanent problem corner, right? So it turns out that all of these 4 algorithms have a way of accounting for this. So there's a way where they will basically, if something goes wrong in the estimates, they kind of have a fail-safe behavior where they will fall back to a different mode of operation or will they adjust thresholds so that they automatically get out of that bad spot. Pro and Charm basically do this by having the threshold tables that are used adjusted based on observations. So there's threshold tables that tells you which relays to use or which transmit rates to use. And there's an initial starting set of tables, but over time these are adjusted based on the observations, in part to calibrate to the hardware that is used and in part for weird environmental effects. Transmit power control has an entirely different set of problems, which is that if you start playing with your carrier sense threshold, and then the receive threshold is often tied to that, you can have nodes that become deaf, right? And so you need to deal with that. And so there's a set of different algorithms that periodically relies on periodic high power broadcasts and periodically increasing that threshold to be able to participate in the protocol. And then Dirk relies on this by using feedback. So if a node observes high packet rates, it will report this to the scheduler, and the scheduler will adjust the schedule to avoid these bad links, right? But it turns out that this is a detail, but a lot of the time in developing these protocols actually goes into getting this fail-safe behavior, right? And different algorithms need to be used for different protocols. So, conclusion. So I talked a little bit about channel emulation, and I always love to talk about the wireless emulator. I think it's a great project. And so I presented 4 techniques which just happen to all use RSSI readings to estimate either received signal strength or SINR. And so these optimizations use that information, but the optimizations are in fact very different in how they use that information. It's kind of my main point. We also need to account for and deal with inaccuracies in these estimates, and that turns out to be actually kind of hard, right? And then there's the issue of how you combine these techniques, right? And this is very interesting. We have a little bit of experience in combining Charm and Pro, right? And it turns out you can actually, we've actually have a multi-rate Pro that uses Charm for rate optimization, and it actually works pretty well. You can do that. It turns out it's easy to prove to you that one does not dominate the other. You need both. So I can be in an environment where there are no relays, right? And then I better have rate adaptation, right? Or I can be in an environment where I really have very high fading or something like that, and rate adaptation is too slow. You know, the changes in the environment are too fast. And then Pro turns out to work because it's very opportunistic on a per packet basis. Okay? And so it turns out that it's easy to show that you need both. Our multi-rate Pro combines the two, but it actually, you could call it the lazy combination of the two systems, and lazy in a good way here, like very little work, right? So the two largely operate independently. The only change that we've made is that we've made rate adaptation on the source a bit more aggressive, because there is a relay there that can back you up if you have a failure. That's kind of the only change we made. There's one other detail that is actually not that important. But I think there's a big issue here. You know, how do I combine DIRC with transmit power adaptation? Wow, that's a great topic to look at. So we'll hopefully be able to do that at some point. So that's the end of the talk. Okay, any questions? Yeah.
So the emulator, is that available for other people to use in terms of hardware, software, or is it sort of a service thing that you can access? Or?
It's a service thing you can access over the internet.
Okay.
So so there's a website, there's some documentation that we're always improving, and you log into this. So if you've used Emulab, then it's a very similar model. Yeah.
We used it for the channel thing.
Yeah, I didn't know how you use it.
We coordinated from here. We were remotely logging in.
Right. Yeah. The biggest hurdle we had with that was that you were using Windows, right? That was the biggest hurdle. And now we support it actually. Now because we use the Emulab software, it supports Windows automatically. So EOR doesn't have to come in the middle of the night and boot manually, right? So any other questions, or people getting hungry for lunch?
Let's thank the speaker.